All right, let's move on to Chapter 3. In this first section, we talk about the complex numbers. So first, before we talk about the complex numbers, let's talk about imaginary numbers here. And your first definition is this: the number I. So welcome to mathematics. I is a number now. Consider the polynomial equation x squared plus 1 equals 0. If you solve for x, you just subtract 1 to get negative 1 over here. X squared equals negative 1. And then take the square root of both sides. When you solve for that, you're going to get x equals plus or minus the square root of negative 1. The negative 1 comes from subtracting. The square root comes from taking the square root to get rid of this square. And the plus or minus comes from the fact that, well, if you plug in positive square root of negative 1 to this, you get 0. If you plug in negative square root of negative 1 to this, you get 0 because the square doesn't care about this. This has to do with function injectivity, that is a function being 1-to-1 and all that, and that's where we get this. We say that numbers with negatives under the square roots are imaginary numbers. Now, why would we call a number like this imaginary? Well, up until now, we've said that negatives under square roots are a bad thing. And indeed, if you want your range to end up being a real-valued sort of thing, then you probably don't want to be getting negatives under square roots. But we're going to allow them, and it doesn't change how you find domains or anything. You still want to watch out for this. This is still something you need to be looking out for if you want a real-valued function. But these are going to be imaginary. Now, why do we call it imaginary? Well, we call it imaginary because we call the other numbers real numbers. All of the real numbers. Well, what's the opposite of something that's real? Something that's imaginary. So there we go. We define the imaginary number I to just be the square root of negative 1. So when you see the square root of negative 1, you can also write I. We will never again use I for a variable. It will always mean the square root of negative 1. So we could have written instead up here that x equals plus or minus I. And it's the exact same thing. Because the square root of negative 1, this surd, S-U-R-D is what this thing's called, negative 1, all of that writing's too much, so we say, you know what, let's just call it I for imaginary. So let's move on to the first example and take a look at it. So here we're asked to write the square root of negative 25 and the square root of 8 in terms of I. Okay, let's start with the square root of negative 25. So the square root of negative 25, by definition, is equal to. Now, we can use some square root properties, because this is just an exponent, is all that this is. This is negative 25, all in parentheses, raised to the 1/2 power. So we can use exponent properties to pull this apart. We can write this as the square root of positive 25 times the square root of negative 1. When you multiply together two square roots, you just multiply their parts together. That's it. So negative 1 times 25 is negative 25. They're both under square roots, so the whole thing will end up being under square roots. Well, now we simplify each part. The square root of 25 is 5. And the square root of negative 1 is, by definition, we said right here, is by definition I. So we say 5i. So instead of root negative 25, we say 5i. We know that this is an imaginary number because there's an I attached to it. That is, it's 5 times the square root of negative 1. All right, easy enough. Let's take a quick look at square root of negative 8. So the square root of negative 8 is the square root of 8 times the square root of negative 1. Okay, this one's a little bit more complicated, but we can break apart. Over here we could do the square root of 25 real quick is 5, because 25 is a perfect square. 8 is not a perfect square. 9 is, but 8 isn't. But can we write 8 as some multiple of a perfect square? We can. It's the square root of, well, I know that 4 is a perfect square, and 8 is just 2 times 4. So let's do that. 2 times 4 times, and we know that the square root of negative 1 is I. Okay. Now, we're going to use the same property that allowed us to break this single square root apart into two different square roots. We're going to use again over here to break this apart as the square root of 2 times the square root of 4 times I. Not the square root of I, just I. Remember, I has the square root. I up here has the square root included in the definition. The square root of I would be the square root of the square root of negative 1, which is the fourth root of negative 1, which isn't at all what we want. So we just simplify what we can here. the square root of 4 is 2. So what we're going to do is write down here, the square root of 4 is 2. We write the whole number first, then the square root, then I. And we can't break down the square root of 2 anymore. This doesn't break down as some number times a perfect square, at least not both of them being integers anyway. So that's it. The square root of negative 8 is 2 root 2 I, is how we read that. Or 2 on the square root of 2 times I. Or 2 times the square root of 2 times I. Or 2 times root 2I. There's a bunch of different ways to read this. They're all valid. So that's all that there is to that. Let's move on to the next example. So before we do this, we need to talk about the complex number. So we talked about imaginary numbers before. A complex number is just the sum or difference of a real number and an imaginary number. It looks like A plus BI, where A is called the real part and BI is the imaginary part. So we say that A is the real part and BI is the imaginary part. A and B themselves, that is A and B themselves, are just real numbers. But remember, when you take a real number and you stick it together with an imaginary number, the whole thing, BI, is an imaginary number. The set symbol for all complex numbers is this blackboard C. And I'll draw it for you here. It looks like this when you handwrite it. That's it. This means the complex numbers. This is the set symbol for the complex numbers. So, let's take a look at this example. It says, write the square root of negative 81 in standard form. Remember, the standard form up here is A plus BI. So let's do that. So the square root of 81, negative 81 rather, is just, well, this is the square root of 81 times the square root of negative 1. And we know the square root of 81 is 9, and the square root of negative 1 is I. Okay? This is not in standard form, however. This is just the imaginary number. Remember, the standard form of anything, up here again, has to look like A plus BI. Well, B is clearly 9, I is I, so what is A? Well, if there's nothing out front, all that we're doing is just adding 0. The standard form is going to look like 0 plus 9I. That is literally it for this example. Let's move on to the next one. So, now we're going to talk about plotting these things. So we're going to plot them on something called the complex plane. So we've got a few points here. 3 plus 2i, 4i, 3, and negative I minus 2 on the complex plane. You've never seen this before in your life, so let me show it to you. It's very easy. So first, let me get a plane here. It looks exactly like this. So remember when I and every other math teacher you've ever had told you please label your axes X and Y, but they're always X and Y, so you never did it? Here's part of why we do this. This is the real part. Okay, this is the real axis, RE for real. This is the imaginary axis. Okay, this is the complex plane. You look at this thing in terms of A, these are your A from standard form, A plus BI. So remember, all of your complex numbers are going to look like A plus B times I. This is your A axis, and this, the horizontal axis is your A axis, and the vertical axis, your imaginary axis, is your B axis. Let me show you what I mean by that. So let's plot 3 plus 2i. It's 3 in the real direction, and 2, positive 2, in the imaginary direction. So we go, watch this, 1, 2, 3 in the real direction, and positive 1, 2 in the imaginary direction, and we plot it right there. So this point that I'm doing is 3 plus 2i. So we label it. That's how you do it. All right? 4i. Remember, I'll write it over here on the right, that 4i, written in standard form, is just 0 plus 4i. So we plot the point 0, 4, basically. So 0, 1, 2, 3, 4, right here. On this is the point 4i. All right? 3. remember, 3 is a complex number. It's just 3 plus 0i. So we plot the point 3, 0. So 3, 0 is right here. That's 3. That stands to reason. It's literally just 3 on the real number line. All we did was cross the real number line with the imaginary number line, and we get this two-dimensional space here that we can work in. Easy enough. Now, here's the one that I can confuse literally everyone with. Negative I minus 2. So we must just plot negative 1, negative 2, right? Think about it. Look, the standard form has the real part first, over here on the right. The standard form has a plus bi. The real part first, then, after that, the complex. So, in this case, what this is actually meaning, and I'll put it down here in quadrant 4 since we're not plotting anything down here, negative I minus 2 isn't in standard form. This is negative 2 minus I. Minus how many i's? Well, minus 1 I. So we're going to plot the point negative 2, negative 1. You need to put this in order. The real part goes first, then the imaginary part, not the other way around. So let's plot the point negative 2, negative 1 and be done with this. Negative 2, sure, negative 1, right there. Here is the point negative I minus 2. Or negative 2 minus I if you prefer. That's it. That's all that there is to plotting complex numbers. If you understand how to do this, you're good to go. So, let's begin talking about complex number operations. So, we're going to find how to do a few things here. We're given two complex numbers. We're given the complex number z, which is just negative 2 plus 3i, and we're also given the complex number, let's do this in red, the complex number w, which is 4 minus I. So we're asked to find what happens when you add together z and w, when you subtract w from z, and when you multiply them. So I'm going to show you how to do addition, subtraction, and multiplication using these numbers. That's easy enough. Let's start with this. Let's start with z plus w. So z plus w is just equal to, well, what was z? Z is just negative 2 plus 3i. Okay, and then we're going to add them. We were asked to add them to w, which was 4 minus I. Awesome. So we're going to add together z and w. This is very easy. All that you do is add their real parts and add their imaginary parts together. That is, you gather like terms, just like you always have. This plus is doing absolutely nothing. This plus in between the two sets of parentheses, that one right there, is doing absolutely nothing. So we can get rid of the parentheses, and this becomes negative 2. This becomes negative 2 plus 3i plus 4 minus I. And then we just gather like terms up. So this is simply negative 2 plus 4 plus 3i minus I. Negative 2 plus 4 is 2. 3i minus I is 2i. That's it. That's z plus w. All right. Z minus w is exactly the same, with one little additional thing you got to watch out for. So I'm just going to write z, which was negative 2 plus 3i, minus, because we were asked to subtract them from each other, 4 minus I. And this time all you have to watch out for is just make sure you distribute this sign. That's it. So then this is negative 2 plus 3i minus 4 plus I, because a negative negative is a positive. And then you just combine like terms. And you can do the extra step of actually getting the like terms together before you do it, or you can just look at it. Negative 2 is real, and so is negative 4. So I'm going to do negative 2 minus 4 is negative 6. All right? And then I'm going to do plus 3i plus I. So plus 3 plus 1 more is plus 4i. So there we go, plus 4i. That's it. We've now subtracted them from one another. And that's all that's going on here. So we now know how to add and subtract them. You just add and subtract them. Basically treat I like a variable. It's not a variable, but just treat it like a variable and know that a real number and an imaginary number are not like terms, and you know exactly what you're doing. So let's take a look at z times w, and let me just clear all this off real quick and see what we can do with z times w. So z times w, that is zw, is just negative 2 plus 3i times 4 minus I, like that. Now, you might be looking at this and you might have some intuition on this, because you've seen binomials before when you were multiplying together two binomials like x plus 1 and x minus 3. So think about it for a second. How would you multiply these two things together? If you said FOIL, or binomial expansion, I'm proud of you, because that's correct. So we're just going to multiply the first terms, the outer terms, the inner terms, and the last terms, and be very careful with what all this means. So let's go through this. We're going to notice something very curious about how I behaves. So, first, the first terms. So we're going to do negative 2 times 4 is negative 8. Okay, we've now done the first term. Let me try to keep up with it up here. Let's do the outer terms next. Negative 2 times minus I is a positive 2i. So we've done the outer terms now. Now we're going to do the inner terms. Positive 3i times positive 4 is positive 12i. And now we need to be careful, because the last term that we're going to do is positive 3i times a negative I. Well, a positive times a negative is a negative. And this is going to be 3 times I times negative I is 3i squared. And so you might say, well, what do we do from here other than just gather up the stuff? Well, we can gather up the stuff, but we can also make a little note. So let's gather up the stuff first. Negative 8 plus 2i plus 12i is just 14i. Okay, and now it's minus this 3i squared term. But we need to do something with this 3i squared term, because you may or may not believe me, but 3i squared, this 3i squared term here, this is a real number, even though it has an I in it. Now, why might that be? Well, let's look over here on the right for a second, and let's look at exactly what I squared is. I squared, remember what I was by definition. I is just the square root of negative 1. So this is the square root of negative 1 squared, because we were squaring I. When you square a square root, they cancel. That is, they are inverse functions. You get just negative 1. That is, I squared just equals negative 1. And that's something definitely worth remembering. All that we did was we squared. We wrote that I squared was the square root of negative 1, and then we squared both sides. So I squared is negative 1, and negative 1 is definitely a real number. So let's come back over here and finish off what we were doing by plugging that little fact in. And that's something you're going to just need to remember. It's going to come in handy every time that we talk about complex numbers. So this is minus 3 times, and then remember, we found over here that I squared was negative 1. So instead of I squared, we're going to write negative 1. Then we're going to finish the problem. So this is just negative 8 plus 14i, my bad, plus 14i, okay, minus 3 times negative 1 is negative 3. Minus a negative is plus a positive 3. And then we combine the negative 8 and the 3 together to get negative 5 plus 14i. So z times w, that is negative 2 plus 3i times 4 minus I, is just negative 5 plus 14i. That is what we end up getting when we do this multiplication. And you need to remember, and this will happen every time, that I squared is negative 1. So, having done that, you might notice that we skipped division. That was on purpose. We'll come back to that later. But for now, let's move on. So let's do a quick little definition here. The complex conjugate. The complex conjugate, this word is pronounced conjugate, of a complex number, z equals a plus bi, so a plus bi is the complex number, we call it z, is z bar, this is read z bar, a minus bi. The complex conjugate of a plus bi is a minus bi. That is, you change the sign on the imaginary part from positive to negative on the imaginary part. Note that z plus z bar and z times z bar are always real numbers. This fact becomes very useful when dividing complex numbers. Z plus z bar, that is a complex number plus its conjugate, and a complex number times its conjugate are always real numbers. That's super useful because everything that we know has to do with how real numbers work, not complex numbers so much. So let's look at this in an example real quick. It says given z is 1 plus 2i rather, and w is 2 minus I, it wants us to find the quotient. That is z over w. So let's look at that real quick. Let's say z over w. By the way, it's very clear when it's typeset what is z and what's a 2. If you all could do me a favor, and I try to do it as well, put a bar through your z so that I know that it's not a 2. We use z a lot. As a matter of fact, you're used to x being used for real numbers. Z is the variable used for complex numbers. So this is a complex number divided by another complex number. What was z? Look back up here. Z was 1 plus 2i, so that goes on top. Okay. And w is 2 minus I. So your intuition might be telling you that this is 1/2, maybe minus I, maybe, because you want to do the 1/2 and you want to deal with this separately. But no, that's not at all how this works. This is 1 over 2 minus I plus 2i over 2 minus I if you want to break this up, and you don't. The secret for doing this, because you can't do it directly, is to turn the denominator into a real number. We need to turn the denominator of this fraction, which is complex right now, into a real number. If you remember, we don't like square roots in the denominator either. Well, now we also don't like complex numbers in the denominator, so that our brains can make sense of it. So we need to turn 2 minus I into a real number. How might we do that? If only there was something up here in the definition that I said that might help us. Oh, if you multiply a complex number by its conjugate, you always get a real number out. So maybe I can just multiply on the bottom by this thing's conjugate. The conjugate of 2 minus I is 2 plus I. That is, I change the sign on the I part from a negative to a positive. Now, I can't just multiply on the bottom by something. I have to multiply top and bottom. But 2 plus I over 2 plus I, that's still 1, and we're still allowed to multiply by it. So let's go through and do it. So this is simply, on top, 1 plus 2i times 2 plus I. And on the bottom, this is 2 minus I times 2 plus I. So you'll notice that this is turned into 2 different multiplication problems. Easy enough. Let's come on down here and write out what this is. So we're just going to FOIL the top and FOIL the bottom. So keep up with me here. I'm going to do 1 times 2, and then I'm also going to do 1 times I. Then I'm going to do 2i times 2 and 2i times I, remembering that I squared is negative 1. So we're going to do all that on the top. Let's do all that on the top. So 1 times 2, the first terms, is 2. 1 times I is plus I. 2i times 2 is plus 4i. And then 2i times I is 2i squared. That is, 2i times 1i is 2 times 1 is 2, and I times I is I squared. Then on the bottom, I'm going to do the same thing. The first term is 2 times 2, which is 4. Then the outer terms, so on the bottom, 2 times positive I is plus 2i. Then in the middle, negative I times 2 is negative 2i. We write our i's last. And then negative I times I is negative, because it's negative times a positive. I'm doing the last term on the denominator. Negative I times I is negative I squared. So now we go through here and we do our cancellations. So we're going to write this up here as, on top, this is 2 plus I plus 4i is 5i. And we know that this is plus 2 times I squared is just negative 1. On the bottom, we note that 2i minus 2i just cancels. So all we're left with is 4 minus I squared, which was negative 1. So now we just finish this off real quick by combining like terms. Come all the way back over to the left. So this is on top 2 plus 5i minus 2, because 2 times negative 1's a negative 2, and plus a negative is just minus all over. 4 minus a negative 1 is 4 plus 1, which I'll write out for you. And then we finish this off. 2 minus 2 is 0. It cancels. You've got just 5i on the top. And on the bottom, you have just 5. And this is just I. So apparently, all of this math happens, and when you divide z by w, you get just I. Everything else canceled. Crazy. That doesn't always happen. In fact, it rarely happens. This happened. Well, maybe you can figure out why this happened. Look at the pattern between z and w, and think about switching the real and imaginary terms and changing some signs around, and you may be able to figure out why exactly that would make sense that it would do something like that. And if you can't, we're going to play around with complex numbers a lot more as we go through the rest of the semester, so we'll get good at this eventually. But remember, the key in the whole thing is this step right here. Multiply by the denominator's conjugate divided by itself, and it will always work out for you. That's how you do every single one of these. So to divide two complex numbers, you simply take the denominator and you multiply top and bottom by its conjugate. That is, change the sign on the imaginary part. Then it's just some simple foiling and remembering that I squared equals negative 1. And that's all there is to that. Let's move on to the next one. So let's talk about functions of complex variables here. It says for f of z equals 3z squared minus z, find f of 1 minus I. So we're plugging in now complex numbers. Well, this is easy. Watch this. F of z, which remember, z is almost always a complex number from now on. F of z is 3z squared minus z, right? Which means that, and here's how I think of this. F of something is just equal to 3 times something squared minus that same something. Well, what were we plugging in again? 1 minus I? Don't think about it too much. We were plugging in 1 minus I, so we plug in 1 minus I here, and we plug in 1 minus I here. Now we just do the math. Don't distribute this 3 in yet, because remember, this is just 3 times 1 minus I times 1 minus I, because anything squared is just that number times itself. So we're just going to have to FOIL this out. And then I'm going to distribute this negative through. So this is negative 1 plus I. Okay? So there's a couple of routes you can go here. You can either distribute in this 3 to this first guy and then do the foiling normally, or you can choose to instead group these up and do this multiplication first and then distribute the 3 in overall. I think that my first option is the better option, but that's not always true, and it's kind of up to you. But I'm going to write this as 3 minus I, or rather 3 minus 3i, I distributed in the 3, times 1 minus I, okay? And then this minus 1 plus I is just going to hang out here for a little while. Let's try not to go past here. So I'm just going to FOIL this out now. 3 times 1 is 3. 3 times negative I is negative 3i. Negative 3i times positive 1 is negative 3i. And then negative 3i times negative I is a positive 3i squared. So that's what all of this first part was. And then we've still got the minus 1 plus I part. Sure, whatever. Let's do one more line down here. This is 3 minus 6i plus, this is 3 times negative 1. And maybe you're starting to get the hint that I squared, all that I squared does is change the sign in front of it, and then the I squared goes away. That's all that it ever does to an imaginary term. We'll start using that trick pretty soon. but for now, minus 1 plus I. So we've got everything together. So this equals 3 minus 6I minus 3 minus 1 plus I. Gather together your like terms. 3 minus 3 cancels. Negative 6I plus I is negative 5I. And then we have a negative 1. And I chose on purpose to write minus 1 minus 5I like that. Maybe you did the math a little different. You did minus 6I plus I is minus 5I minus 1. That's fine, but that's not in standard form. Because you might think to plot this, you go plot the point negative 5, negative 1. You don't. It's the point negative 1, negative 5. A little different. Try to write this in standard form when you get your answer. Write the real part first, then the imaginary part. So that's minus 1 minus 5I, or negative 1 minus 5I if you prefer. But that's it. That's all that it is. So f of 1 minus I is negative 1 minus 5I. That is the most correct way to write this, is f of 1 minus I equals negative 1 minus 5I. Now, think to yourself for a moment. Every time that I plug in a complex number, am I necessarily going to get another complex number out? Always. No. We've seen, like, for instance, right over here, that it's possible, through some operations, to turn what looks like a complex number, I, into a real number, just by squaring it. So it doesn't always work out that way, it just usually does. But functions of complex variables aren't that difficult. You just plug it in and do whatever it is that you're supposed to do from the rules before in order to work with complex numbers. And as always, don't get overwhelmed when you see a new topic. Just dig into it, do the practice, make a few mistakes, learn from your mistakes, and pretty soon this will be second nature to you. But for now, we move on. So, let's talk about the cyclic powers of I. That is, it goes in a cycle. So we're going to notice the pattern for I squared, I cubed, I to the fourth, and we're going to use it to find I to the 96th power and I to the 175th power. We've already talked about I squared, but we're going to go through it again. So I'm going to write all of this over here, and then we're going to summarize it, and then I'm going to do the second part. So first off, let's talk about I. This is I to the first power, if you want to think of it that way. So think about it this way. I equals I to the first power, which is just the square root of negative 1. I squared is just I times I. By definition, anything squared is that number times itself. That's the square root of negative 1 times the square root of negative 1, which is the square root of negative 1 squared, which is negative 1. That is, I squared is negative 1. Okay? Now, watch this. We can write I cubed as I times I times I. But then we can also just group together, if you prefer, these first two i's and say that that's just I squared times I. I hope you'd agree with that. That I cubed is just I squared times I. When you multiply like bases, you add exponents. And 2 plus 1 is indeed 3. And why is that useful? Because we know what I squared is. I squared is negative 1. This is negative 1 times I, or just negative I. Let's look at I to the fourth. This is I times I times I times I. And we can group together these i's and these i's. And we know that that's just I squared times I squared. I'm just writing it in terms of things I already know. Well, I squared is just negative 1. So this is negative 1 times negative 1, which is just 1. So let's look at I to the fifth. Well, you may notice that I to the fifth is I times I times I times I times I. But we can just group these first 4 together. Because now we know that this is just I to the fourth times I. Well, I to the fourth is just 1. We just found it. So this is just I overall. So now we're back to where we started. And I'm going to do one more so that you can notice the pattern, but this is as far as I'm going. I to the sixth by this same logic we used up above, is it's just I to the fourth times I squared. I to the fourth is just 1. I squared is just negative 1. So this is just negative 1 again. So look here. The pattern goes like this. I, negative 1, negative I, 1, I, negative 1, and it continues forever. So there's only really 4 distinct things that I can do when raised to a power. It can either be I, negative 1, negative I, or 1. That's it. So make sure that you get all that down. Pause the video for a second. It's worth writing. But I'm going to rewind here, and we're going to talk about exactly how to use this to find incredibly high powers of this, because that was a lot of writing just to find a few of these. So let's think I to the 96th. How can we write I to the 96th and I to the 175th? Remember, when we did I to the 4th, that's just 1. That's going to be our key. So let me write down over here, first off, that I to the 1st is I, that I squared is negative 1. This is very much worth having written in your notes so that you can use it. I cubed is negative I, and I to the 4th is just 1. This last one, the I to the 4th equals 1, is the big deal. So what we're going to try to do is basically divide out as many multiples of 4 as we can from any given number before we can find anything. For example, let me give you an even easier example before we hop into these big boys here. Let's do I to the 9. We can write 9 as 4 times some number plus some other number. Would you agree that 9 is just 2 copies of 4 and then 1 more? That is, 9 divided by 4, that is, 9 divided by 4 is 2.25. Or if you want to write this as a mixed number, it's 2 and 1 over 4. By definition, that means that this is 2 copies of 4, okay? And this 0.25, or 1/4, means plus 1 more. Okay? So we can write 9 over 4 as, or rather we can write 9 as 4 times 2 plus 1. That's just 8 plus 1, which works. So that's neat. So that's all that this is. This is I to the 4 times 2 plus 1. How is that useful? Just using exponent laws is how that's useful. This is, by definition, then, just I to the 4 times 2 times I to the 1st. Remember, when you multiply like bases, you add exponents. So we can break apart this addition as a multiplication of their bases. And if you need help remembering your exponent rules, I'll write them out for you real briefly right here, and you can copy them down because they're probably going to get erased here in a second. But we can do this. Basically, any base, so let's say x, for example, x, okay, x to the a times b, that was just x to the a raised to the b power. And that's a terrible looking a. Hang on. X to the a to the b power. That is, power to a power, you multiply powers. You probably learned these the other way around. We're using this to break it apart. X to the a plus b is x to the a times x to the b. That is, you learned it backwards. You learned it when you multiply like bases, you add exponents. Well, when you add exponents, you can also multiply like bases. That's the 2 big rules that we're using here. So, let me rewind for a moment, and let's talk about this over here. Why is this useful? We're just going to use those properties real quick. This is I to the 4th squared times I. We know that I to the fourth, look here, I to the fourth is 1. So this is 1 squared times I, which is obviously just I. So I to the ninth is I. That's how you do that. So now, all we're going to do is try a much larger number. Let's do I to the 96th. I to the 96th. Okay. So here's how I'm going to do this mentally. I'm going to multiply 4 by numbers until I get as close to 96 as I can get. I'm going to start with a very easy number, 20. I know that 4 times 20 is 80. So maybe I need to add in, say, 3 more of them. So 4 times 23 will get me a little bit closer. That'll get me up to 92. And then can I actually do another one? 4 times 24 is 96. If you don't believe me, go do the math on it. You do indeed get 96. So then this is just I to the 4 times 24. If you want to do this some other way, you can literally just divide, since we're wanting to work off 4s, you can literally just divide 96 by 4 and you'll get 24. That means that, by definition, 96 is 4 times 24. Well, this is just I to the 4th to the 24th power, using that rule. When you multiply powers, that's the same as raising one power to the other. Why did we group it together as I to the 4th? Well, because I to the 4th is just 1. And 1 to any power is 1. 1 times 1 times 1, 24 times is just 1. So I to the 96th is just 1. Okay, that was an easy example. We didn't even have to add anything to it. Fine, Mr. Bryant, you say. I'm not challenged by this. Let's do something a little bit harder. Okay. Let's look instead at I to the 175th. So, now we really got to start working at this. The easy, quick, and dirty way to do this is just to do a little bit of division. I'm going to show you using the hard way first, which isn't even that hard. I'm going to try multiplying numbers times 4, and I'm going to get as close to 175 as I can without going over it. This is how you do it without a calculator. So let's try just a really big number first. Let's multiply it by 100. Well, 4 times 100 is going to be 400, and that's way too big. So maybe I multiply it by 50. So 4 times 50 is 200. That's still too big. So let's try, 40. 4 times 40 is 160. That's not big enough. So maybe I need to add in a few more copies of 4. So I can do it one at a time if I want to. So 4 times 41 is 164. Okay. 4 times 42 is 168. 4 times 43 is 172. And if I add in one more copy of 4 to this, I'll get 176, which is too big. So we know then that 175, so this is I to the 175 is just 172, which is 4 times 43. Okay, plus, how many more do I need to go? Well, I'm at 172, so I need 3 more. So it's 4 times 43 plus 3, which means this is I to the 4 times 43 times I cubed. When you add exponents together like this, you can just multiply their bases. Well, this is I to the 4th, 43 times I cubed. Well, we know that this is just 1 to the 43rd. And we know that I cubed, look over here, I cubed is just negative I. So that's just negative I. 1 to the 43rd is 1. The whole thing is just negative I. Remember, when you're doing these, you only have 4 possible answers. I, negative 1, and 1. Or in order, you have I, negative 1, negative I, or 1. Those are your only possible answers. So you're going to get one of those 4 answers out. If you get anything else, you did something real wrong. Now that's the hard way to do this. Let's rewind and think about how to do this with some real simple division. Now, you can do long division if you want to, and go through and figure out 175. All right? Or, if you have a calculator handy, for very large values like this, I've showed you how to do it by hand. Let me show you how to do it on a calculator. If you go do 175 divided by 4 and a calculator, you'll get a number out. But I don't have a calculator here, so let's just literally do, and this is worthwhile. We're going to be doing long division with polynomials here in a bit, so let's do 4 into 175. 4 goes into 17 how many times? It doesn't go into 1 at all. So 4 goes into 17 4 times. 4 times 4 is 16. Subtract. You get 1. Bring down your 5. Okay. 4 goes into 15 how many times? Well, 3. That'll give you 12. Right? 3 times 4 is 12. And you get 3 as a remainder. That is, it's 43 is your quotient, 3 is your remainder. Oh, so then we can write 175 as your quotient, 43, times the thing you divided by, your divisor, 4, plus your remainder. Always. We'll always be able to do that. So the number on top of the actual division times the number you divided by plus your remainder. This is actually called the remainder theorem, and it's something that we'll talk about later in class, but it's useful. You can write any number like that as the quotient times its divisor over its remainder. You'll always be able to do that. And we know, basically, that the 43 times part, we know that this is going to be I to the third. That is, all of this dies in a fire. We know that it dies in a fire because we're using this fact over here, that I to the fourth equals 1. So this is I cubed. Go look it up on your list. It's negative I. That's it. That's all there is to this. And for the sake of argument, I want to do one more of these real quick, even though it isn't listed here. I want to do I to the, and let's do some stupid number, 1,977, 1977. Was that a good year? I don't know. I wasn't alive. But let's do this. So we're literally going to do 4, because we want to make use of this fact, because multiplying 1 times itself a bunch is useful. So we're always going to divide 4 into whatever this number is, 1977. And let's just do the long division. 4 goes into 19. Let's see here. 4 times. 4 times 4 is 16. Subtract these. You get 3. Bring down the 7. Okay. 4 goes into 37. 9 times. 9 times 4 is 36. Subtract them. You get a 1. Bring down the 7. And 4 goes into 17, which is what happens when you bring this in, 4 times. 4 times 4 is 16, and you get a remainder of 1. So then we can write this as I to the, and we can write 1977 as 4 times 494 plus 1. This is the same thing as I to the first power. All we care about is this. Because we wrote the rest of this as a multiple of 4, it's all going to die in a fire. And by that I mean it's going to turn to 1, and we're going to be raising 1 to the 494th power. That's just 1. So this is going to be I to the first, which is just I. We're working what we call modulo 4. And that's something you'll learn way, way later in a perhaps in a discrete math class or a number theory class or abstract algebra. At some point, if you go very far in math, you'll learn more about modular stuff or into computer math as well. But for now, this is very simply how to do this. You'll always be able to write it as I to the whatever you divided by times whatever was on top plus whatever the remainder was. And it's the remainder that we care about. If the remainder is 1, then it's I. If the remainder is 2, then it is negative 1. If the remainder is 3, it is negative I. If the remainder is 0, that means it divided in evenly, like I to the 96 is. And so you're going to get 1 out. Because if your remainder ended up being 4, then you can actually divide 4 into the number one more time, and you'll just go through it one more time. Literally just do a little bit of long division and look at your remainder, and that's it. But anyway, that'll end us for today. I'll see you back here when we get to section 2.